Up next, it is my pleasure to introduce Martin Millon. Martin is an SNSF fellow joining us here at KIPAC. And today he's going to be telling us about a rare case of gravitational lensing by a quasar. Take it away, Martin.
Hi, everyone. Martin Millon, a postdoc here. I'm going to speak to you about this rare case of strong lensing by a quasar and like a future project that we are having here related to this system. So what I will not talk about is lens quasars, when the quasar is in the background, lensed by the foreground galaxy and forming like multiple images. Those are really useful for measuring the Hubble constant, staining dark matter, for example, or even the accretion disk of the quasar itself. We know about like 300 of those systems, but in my case, the quasar is actually in the lens plane. It's in the foreground, and those systems are much rarer. We know only 3 of them. And they are useless for cosmology, but they're really interesting if you want to study the relationship between the black hole and its host galaxy. So I will focus on this system, G0919. This is playing. Yeah, so this system. It's a very special one because the quasar is seen as a substructure of a more massive galaxy, which is acting as a lens. So most of the lensing effect is coming from the nearby massive galaxies, and it's lensing background star-forming galaxies at redshift 0.55. So this blue galaxy that is lensed by those 2 systems. But the quasar and its host are still massive enough to slightly disturb the gravitational arcs and leave like a lensing signal that we can use to measure the mass of the host of the quasar. So yeah, so here you see like a slight imprint by the quasar and its host on the gravitational arc. Yeah, with the main galaxy here and the quasar host. So we modeled the system. We fitted like the mass of in the lens plane, the light in the source plane, fitted everything at the same time, and got a very precise measurement of the host of the quasar host mass at 16% precision. And why do we care about this? Why do we need to measure the mass of the host? It's because locally we observe this very famous like M sigma relation, so the relation between the black hole mass and the mass of its host, which is surprising because if you do the math, you compute the gravitational sphere of influence of the black holes, it should be like a few hundred parsec at the center of the galaxy. The galaxy is much bigger, so the galaxy shouldn't feel the black hole in the center. But to explain this correlation, several mechanisms has been proposed. A successful one was AGN feedback in a numerical simulation, where actually the energy input in the galaxy by the black hole when it was active as a quasar was controlling the growth of the galaxy, and you could like reproduce those correlation by introducing AGN feedback. Or another theory could be like just if the most massive black hole were living in the most massive halo at the beginning, you could like conserve those correlation across redshift through the assemblies of the halo and the merging of the black hole. So what you really want to do is to study those correlation not only locally but across redshift. But the problem is that like it's very difficult to measure the mass of the galaxy at a higher redshift. But lensing is really efficient and it's really accurate and precise at those redshift. So here is the data point that we had with 0919. You see the error bars are much more smaller than for other AGN measured with conventional techniques. We also measured the stellar mass of the host from the photometry, and you see that it's light on the relation. That's only a single data point, and if we want to study those relations across redshift, you will need a bigger sample. And that's a project led by Everett MacArthur here as a postdoc fellow at KIPAC, looking for more of those systems in DESI. So how do we do? Then you look at anomalous spectrum of quasar in the DESI dataset, where you have like emission line at a higher redshift than the quasars. So here, for example, this is a spectrum of 0919, where you see the broad line of the quasar at redshift 0.2. This is a normal quasar spectra, but you see a set of emission line at a higher redshift coming from the source galaxy. So you see, for example, those O3 emission at the redshift that doesn't match with the redshift of the quasar. And since the SDSS fiber is only like 1.5 arcsecond across, it means that the emission is very close, especially, and that it means that you have a very high probability of lensing. So we're going to look for those systems in DESI with the help of machine learning to try to find more of those systems and build a sample of those quasars acting as gravitational lensing. So we'll leave you with my conclusion here and take a few questions. Thank you.
Okay, thank you, Martin. Any questions? Tom, and then Andrew afterwards.
Oh, really interesting. So on the last point you were saying, you have a very high likelihood of lensing. Can I get you to be a bit more quantitative and tell us how you think about it?
3 out of 4. We had 4 candidates. 3 of them were confirmed with HST. So that's a very small number statistic, but at the kind of rate that you could expect.
And Andrew.
Thanks for the talk, Martin. I have a very similar question, and I'm wondering if you have like a spatial density rate for these types of quasars.
Yeah, so you could compute the lensing probability of the system. You take a halo mass distribution, you compute the size of the caustic projected in the source plane, compute the lensing efficiency. You can make all those computations. They are hard to track. It's been computed, like in Euclid, you should find around 900 of those systems. In HSC, you should find like a few dozens with imaging. But with spectroscopy, it's much harder because it all depends on how you select your quasars. And I think for now, spectroscopy is the way to go because like observing them in imaging survey is really hard because the Einstein radius is very small, so it's really hard to resolve. So you need a space survey. But in spectroscopy, the rate, so it's empirical, and the rate is like about 1 in 10,000 quasars is acting as a lens, at least in SDSS. So I expect something similar for DESI.
But if I can ask a slightly leading question, perhaps based on recent claims in the literature, when you have these quasars doing the gravitational lensing, do you think there's any useful information about the supermassive black hole in the lensing signal?
Yeah, so in our case, no. So in this case, the mass of the host is about 10 to the 10, and the mass of the black hole is 10 to the 7. So at 10 to the 7, you basically have like no strong gravitational lens signal at all. So basically, I mean, we fitted also like a model where you have like the mass of the host, and we added a point mass in the middle, but basically the mass of the point mass is unconstrained. So we don't constrain the black hole mass with this technique. But yeah.
Sure, thanks. And if there's no more questions, let's thank Martin again.